Welcome to this extended review of AI-powered neuroelectromagnetic source imaging, a transformative framework that leverages the synergy of advanced physics-based models and artificial intelligence to reconstruct the brain's electrical activity from non-invasive EEG and MEG measurements. In this video, we'll explore how this approach overcomes challenges of traditional neuroelectromagnetic imaging techniques, such as noise sensitivity, computational inefficiency, and limited interpretability. Through cutting-edge AI tools, such as convolutional neural networks, CNNs, and physics-informed neural networks, PINs, this method enables highly accurate and scalable, opening new horizons for neuroscience and clinical diagnostics. AI-powered frameworks have transformed this domain, leveraging deep learning approaches like convolutional neural networks, CNNs, to extract meaningful spatiotemporal patterns from high-dimensional EEG/MEG data. These models capture critical relationships in neural activity while overcoming limitations of traditional methods. By employing parameter sharing and sparsity principles, CNNs are computationally efficient and robust to data variations. In addition, advanced model interpretation solutions which enhance the transparency of these methods by uncovering links will be explained. Rather than treating neural decoding as a black box, modern approaches use spatial demixing and autoregressive models to identify the temporal progression and relationships between neural sources. Traditional direct inversion schemes, DIS, rely on physics-based models to solve the source imaging problem. While foundational, these methods face challenges like noise sensitivity and computational demands. Recent innovations, such as physics-informed neural networks, PINs, merge physical modeling with neural domain knowledge directly into the learning process. These hybrid models improve generalization and allow for more accurate source reconstructions. Finally, spatiotemporal neuroelectromagnetic frameworks combine spatial modules for cortical mapping and temporal modules for dynamic brain activity modeling. These AI-driven applications ranging from functional brain mapping to real-time patient monitoring, representing a transformative leap in neuroscience and clinical diagnostics. The applications of this technology span from real-time functional mapping to advanced monitoring and diagnostics in clinical settings. Let us dive deep into each aspect of this work. This comprehensive integration of AI and neuroscience opens new horizons for understanding and decoding the human brain, pushing the boundaries of neuroelectromagnetic source imaging. At the core of neuroelectromagnetic imaging lies the analytical solution of the neuroelectromagnetic problem, structured around two key components, the forward problem path and the inverse problem path. The forward problem is fundamental. It computes how neural currents within the brain generate measurable electromagnetic signals on the scalp. This involves volumetric current reconstruction, mapping the distribution of electrical activity throughout the brain's volume. Impedance inversion, estimating the electrical conductivity of different brain tissues, which is essential for precise modeling. Surface voltage computation, relating internal neural activity to the MEG signals on the scalp. The forward path relies heavily on sophisticated numerical techniques, such as finite element method and finite difference time domain. These tools account for the brain's complex geometry and varying tissue properties. The stiffness matrix, which represents the relationship between and observed potentials, ensures mathematical rigor in these calculations. The inverse problem, on the other hand, reconstructs the underlying neural sources based on measured EEG/MEG data. This is inherently more challenging, as it is an ill-posed problem where small changes in the data can result in vastly different solutions. To tackle this, two primary modeling approaches are employed. These provide a comprehensive map of neural activity across broader brain regions. Dipole models, these offer detailed localization of specific neural sources. At the biophysical level, the inverse path estimates current source densities, while at the physiological level, it models the interactions between neural populations like neural mass models. To ensure accuracy and stability, the optimization framework integrates a data fidelity term, which minimizes the error between modeled and observed signals, and a regularization term, which constrains the solution space. Together, the forward and inverse problem paths form the backbone of neuroimaging, enabling precise and interpretable reconstructions of brain activity. The origins of EEG and MEG signals lie in the synchronous activity of large populations of neurons, particularly pyramidal cells in the cerebral cortex. These neurons generate transmembrane currents during synaptic transmission, producing electric potentials and magnetic fields that propagate through the brain to the scalp. To signals effectively, the framework employs convolutional neural networks, CNNs, which excel at extracting spatiotemporal patterns from high-dimensional data. The advantages of CNNs include parameter sharing. Learning shared filters across the input reduces computational complexity, making the approach scalable. This principle captures localized patterns in the data, which are essential for understanding neural activity. Invariance to local translations ensures robustness to small shifts in input data, making the model reliable under varying conditions. The CNN pipeline involves several stages: problem formulation, G/MEG data for neural network processing, data acquisition and pre-processing, cleaning and preparing the data for feature extraction. Feature extraction, using convolutional layers to identify meaningful patterns in the data. Model design and evaluation, designing neural network architectures accuracy and efficiency. By linking decoding outputs to biological mechanisms, CNNs bridge the gap between traditional black box approaches and interpretable models of neural dynamics. The direct inversion method is one of the foundational approaches in neuroelectromagnetic source imaging, offering a direct solution to the inverse problem of reconstructing brain activity from EEG or MEG measurements. This method relies heavily on solving the forward problem, which involves calculating the relationship between neural current source and the resulting electrical potentials or magnetic fields measured on the scalp. The lead field matrix and forward path is computed using precise electromagnetic numerical methods like the finite element method, the method of moments, or the finite difference time domain method. These numerical methods enable accurate modeling of the head tree and the varying electrical properties of its tissues. Software tools such as FieldTrip and Brainstorm are widely employed to solve the forward problem and generate accurate lead field matrices. Once the forward problem is solved, the inverse problem aims to estimate the source currents from the measured signals. Despite its widespread use, the direct inversion method has notable limitations. It is highly sensitive to noise, particularly for sources located deep within the brain. The need for explicit regularization terms adds a layer of complexity, requiring expert intervention to fine-tune parameters for each dataset. Furthermore, the computational burden of solving the inverse problem iteratively can be significant, especially for high-density EEG or MEG systems. These factors can also constrain the spatial resolution of the reconstructed sources, as volume conduction effects and low signal-to-noise ratios limit the method's ability to localize activity. Nevertheless, the direct inversion method remains a cornerstone in neuroelectromagnetic source imaging, laying the groundwork for more advanced techniques such as AI-based frameworks. It continues to be used in numerous applications, including brain-computer interfaces, functional brain mapping, and pre-surgical planning for epilepsy. By combining precise analytical modeling with powerful numerical techniques, the method has paved the way for modern advancements in brain imaging while addressing critical challenges in neuroscience and clinical diagnostics. Interpreting neural activity in the context of EEG/MEG inverse problems requires going beyond black box approaches. Instead of simply decoding outputs, XX, from brain activity as a naive black box, advanced frameworks aim to model the latent source dynamics. Traditional approaches to neuroimaging often treat the reconstruction process as a black box, focusing solely on outputs without interpreting the underlying mechanisms. Modern frameworks, however, aim to uncover the latent source dynamics that drive these signals. Latent sources are modeled using autoregressive dynamics, which capture the temporal progression. The relationship is demonstrated in this slide. To model EEG/MEG data generation, the observed signals are expressed as mixtures of latent sources as shown in the slide, where C is the spatial mixing matrix, and omega accounts for noise. Spatial filters reconstruct these sources, interpretation of the neural dynamics. This gray box approach blends domain knowledge with advanced neural models, enabling the interpretation of how neural signals propagate from their cortical origins to measurable scalp activity. By combining spatial and temporal modeling, these frameworks enhance the understanding of brain dynamics and improve localization. By combining spatial demixing, temporal convolution, and advanced activation functions, this gray box approach enables more transparent and meaningful reconstructions. One of the most advanced AI-powered approaches for neuroelectromagnetic source reconstruction is the spatiotemporal framework, exemplified by methods like DeepSIF. This approach leverages deep learning and synthetic training datasets generated from biophysically inspired neural mass models, offering significant advantages over traditional methods, such as direct inversion or optimization-based techniques. Spatiotemporal AI frameworks bypass the need for explicit regularization by implicitly learning spatial and temporal priors from large-scale synthetic training data. These data, generated by realistic biophysical models, capture the complex dynamic, enabling the deep learning framework to generalize well across different datasets and conditions. By combining spatial modules, such as ResNet blocks for processing EEG/MEG scalp distributions, with temporal modules, such as LSTM layers for capturing temporal dynamics, these methods achieve a higher resolution than conventional techniques. The advantages of spatiotemporal AI frameworks are multifaceted. They demonstrate improved accuracy, overcoming challenges like volume conduction effects and low signal-to-noise ratios, particularly for deeper brain sources. Their robustness across various noise levels and testing scenarios ensures reliable performance in challenging conditions. Furthermore, these methods are computationally efficient, providing rapid inference after training without the need for manual hyperparameter tuning, making them suitable for real-time applications. Their generalization capability allows them to effectively map sensory and cognitive responses or identify regions, such as epileptogenic zones, across diverse patient populations and experimental setups. This novel approach represents a transformative leap in electrophysiological source imaging, addressing long-standing limitations of traditional methods while paving the way for advanced applications in neuroscience research and clinical diagnostics. In this slide, we delve into the improvement of the forward and inverse neuroelectromagnetic problem using a Bayesian perspective, advanced by integrating physics-informed neural networks. This novel approach brings together the predictive power of AI with the theoretical rigor of physics and Bayesian frameworks. The forward and inverse problems on deterministic methods that often struggle with the uncertainties inherent in spatiotemporal neural source imaging. By incorporating Bayesian inference, we explicitly account for these uncertainties, enabling a probabilistic approach to neural source reconstruction. This framework introduces PINN-based inverse mapping, which combines concepts. Information field theory provides a probabilistic framework for modeling and reconstructing spatiotemporal fields, such as neural activity distributions. IFT treats neural source localization as a stochastic process, capturing uncertainties in measurements and modeling assumptions. Information geometry extends Bayesian analysis by exploring the geometric properties of the probabilistic space, allowing for more efficient localization and reconstruction of neural sources. It provides insights into the structure of the source space, enabling the framework to adapt dynamically to varying spatial and temporal resolutions. These tools enable the framework to localize spatiotemporal sources with greater precision and reliability. By embedding domain-specific physical knowledge into the Bayesian perspective, the PINN-based approach ensures that the forward problem generates realistic training data, while the inverse mapping accurately reconstructs neural sources. This combination addresses the challenges of noise, ill-posedness, and complex signal propagation. With this enhanced framework, applications in real-time monitoring, functional brain mapping, and diagnostic imaging are poised to benefit from significantly improved accuracy and robustness. This marks a critical step forward to decode and understand brain activity. This integrated approach represents a significant advancement in neuroelectromagnetic imaging, bridging the gap between physics-based modeling and AI-driven methods, and offering a robust and scalable solution for spatiotemporal source reconstruction. In conclusion, AI-powered neuroelectromagnetic source imaging is revolutionizing our ability to understand and decode the human brain. By addressing the challenges of traditional methods, this framework offers a robust, scalable, and interpretable solution. As we advance, this synergy between physics, neuroscience will undoubtedly unlock new frontiers in brain imaging.